Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 4 chemistry students. Welcome back. I'm Alan, still with you in chemistry lessons. So we are still on topic 3, the periodic table, and unit 12 about chemistry of group 7 elements. This time we are heading in for lesson 4, which is about compounds of group 7 elements and tests for the halide ions in solution. That's what we're going to focus on. So, before we get started on today's lesson, let's take a quick check on what we looked at in the previous lesson, then we come back and continue. We looked at the displacement reactions of the halogens and the halide ions briefly and said chlorine displaces bromide and the iodide, as you see, because it is more oxidizing agent. Then bromine only displaces iodide ions and not chloride because its strength does not outweigh that of chlorine. Then iodine, because it is a poor oxidizing agent, does not displace either of the bromine or chloride from its solution. So as you see the observations, when you add different components into those test tubes having solutions of the halide ions. That's what we looked at last time, and that is about the summary of oxidizing and reducing abilities. Now, lesson 4, we are looking at compounds of group 7 elements, then we test those halides in solution. The focus in here will be on the hydrides of group 7. Basically what we call the hydrogen chloride, hydrogen bromide, hydrogen iodide, and hydrogen fluoride. That is what we shall look at in terms of the compounds. We shall not look at any other. So we shall look at the general properties, then we look at the method of preparation. From that point, we can see the lesson objective. It is one, but of course encompassing all the general properties. So by the end of the lesson, you should be able to describe and illustrate the behavior of hydrides of group 7 elements in regard to volatility, that is in terms of change in the physical state, acid strength, and the thermostability. In other words, if you get like hydrogen chloride and you compare it with hydrogen bromide, which one resists decomposition when heated? That is what we mean by thermostability. So that is the objective, and that is what we're going to focus on much of today. Let's look directly onto the general properties. Take a close look. Look at the highlighted, at the red ink. We have the hydrogen halide, that is HF, HCl, HBr, and HI. We have their physical states at temperature below 20 degrees. There is a reason for that. In brief, it's because above that, then we shall have exceeded the boiling point of hydrogen fluoride, indicating it will exhibit a different physical state. So at temperature below 20, hydrogen fluoride is a liquid, the rest are gases. You see the boiling points, you see the bond length, and the bond energy. Unlike the other groups that we've looked at, which were involving of metals, then a mix of metals and nonmetals, these are completely nonmetals, so they form mostly covalent bondings or covalent bonds with other nonmetals. That's why we are bringing in the issue of the bond length and the bond energy. When we come to the these properties, the bond length and the bond energy, have to be incorporated, so we need to look at them in details. Now let's start on the physical state. Like as we said, hydrogen fluoride is a liquid. You see its bottle in here, but the rest are gases at room temperature. Normally, the room temperature conditions, we take between 20 to 25. That's the range of room temperature due to the changes in the environment. So the question is, why is it a liquid whereas the rest are gases? It's because of the hydrogen bonds. Hydrogen bonds in hydrogen fluoride. Remember, we talked about it as a unique property for fluorine at the start. So this is what happens. When you're having fluorine bonded to hydrogen, due to its high electronegativity, the bonded electrons are more towards fluorine, and this creates an equal distribution of electrons between fluorine atom and hydrogen atom. The end product is you will have fluorine having more electrons compared to hydrogen. So this creates a higher positive charge on hydrogen atom, which we term as partial positive, in regard to fluorine having a partial negative because of more electrons. So in presence of another fluorine molecule with lone pairs or unbonded electrons, the partial positive charge of hydrogen or the high charge density of hydrogen, it will be attracted, or it will attract the negative charge on the fluorine molecule. In that way, they create a force of attraction. This is specifically called hydrogen bond, and it exists in molecules of hydrogen bonded to oxygen, nitrogen, and fluorine because they are the most electronegative atoms. So the formation of these hydrogen bonds make hydrogen fluoride to exist as a liquid because they are stronger. Let's make a comparison with the rest. The rest, they have dispersion forces of attraction, as you see, also due to an equal distribution of electrons as a result of difference in electronegativity. The point to note in here is due to the high value of electronegativity of fluorine, it creates in hydrogen bonds, whereas in there it's simply dispersion forces. So, and the point to note at the end, above 25, they all exist as gases because you've noticed that hydrogen fluoride has a boiling point of 19.9. So above 20, it will be a gas. Let's look at the trends in the boiling point. Still, we shall have to involve in the intermolecular forces of attraction. As you can see, the trend, apart from fluorine, the rest, it increases down the group, but for fluorine, it is exceptionally high. It is the only halogen halide with a positive value as boiling point. The rest are negatives. So the same explanation, presence of hydrogen bonds in hydrogen fluoride, whereas the rest, they have dispersion forces of attraction. And as we looked at them, at the creation of dispersion forces in the first lesson of group 7, you notice it increases with increase in the molecular size, of course, which comes with increase in the number of electrons. So from hydrogen chloride to hydrogen iodide, the number of electrons go on increasing, or the molecular size goes on increasing, and so the strength of the dispersion forces that will be created are expected to be much higher. That is about the trend in the boiling points. Now, let's look at the bond length and the bond strength. Yeah, you still recall bonding in your other previous lesson. whereby you looked at the orbital overlap. And this is exactly what happens in here. So when we talk of bond length, we mean the distance between the orbital of hydrogen and the orbital of whichever atom is bonded to. In this case, the fluorine, chlorine, bromine, and iodide. Check the illustration in here. So this is normally indicated with that dash, H-F, or this, that is the length we are talking of. So what do you see? Look at the bond length. Look at the values in nanometers. You see it is increasing downwards. As you move from hydrogen fluoride to hydrogen iodide, the bond length increases. It is even seen from this illustration. Look at the atom of hydrogen and compare with the atom of iodine. Look at the gap between the two atoms. Compare it with the gap between here. So what is the trend? It increases downwards. Why? Because as you move from fluorine to iodine, you're increasing the size of the hydrogen atom. As the size increases, then the bond length also increases because this hydrogen will have to bond with the outermost electrons in here. So from the nucleus to the outermost electrons, you have a bigger gap. The end product is, as the electrons are being shared, as you see these dots, they are far away from iodine atom, in the same way from the hydrogen atom. So we have the bond length increasing due to the increase of the size of the hydrogen atom, simple. Let's look at the bond energy. Let's look at the bond energy. What do you see? As the size becomes longer, the bond energy decreases. Of course, when we talk of bond energy, we mean the amount of energy required to break a bond, one single bond in a covalent molecule. In this case, these are covalent molecules. So to break a bond between hydrogen and chlorine or hydrogen and bromine is what we mean as the bond energy, the kilojoule per mole, this single mole of the hydrogen halide. So the energy needed to break it. As you can see, it decreases down the group as the length becomes longer. So, meaning the bond strength also decreases. And that is the trend we are looking at. Same explanation. Increase in atomic size increases bond length, which decreases the force of attraction. In this case, we call it the dipole attraction, partial positive and partial negative. And so the strength decreases, requiring less energy to be broken, and that is the value you see in here. Let's look at one other property, the thermostability. Thermostability, of course, this also goes back to the bond length and the bond strength. So if you require too much energy to break the bond, then that molecule will be more stable on decomposition. And if you require less energy to break the bond, then that molecule will easily decompose when you apply some heat. And that is what happens. The trend in thermostability decreases. In other words, hydrogen fluoride doesn't easily decompose because it requires a lot of energy to break the bond compared to hydrogen iodide or hydrogen bromide. So the decomposition in here is break this molecule into its respective components, as simple. Same explanation. Bond strength related to bond length, and of course related to the size of the atom, especially the halide, the hydrogen atom. So that is about the thermostability. It decreases down the group due to decrease in the bond strength as the size of the halogen increases. You see the values. Lastly, let's look at the acidic strength. That is for the physical properties. Of course, when we talk of acid strength, I can't fail to remind you, you always talk of hydrochloric acid, hydrobromic acid, you saw hydrofluoric acid, and hydroiodic acid. Those are actually acids, but the commonly used acid is hydrochloric acid. I think at this moment, everyone knows of hydrochloric acid. So when you get these hydrides of group 7 and you dissolve them in water, they release hydrogen ions. And the presence of these hydrogen ions in solution is the reason for the acidity. So when we're talking of the acidic strength, we look at how is this molecule going to release hydrogen ions. If you have hydrogen fluoride, as you noticed, with its high energy required to break the bond, and hydrogen iodide, which one would easily set free hydrogen ions in solution? Yes, of course, the hydrogen iodide, because the bond is weaker, it can easily be broken. And this takes us to the acidic strength. It increases down the group, meaning the hydrogen iodide is actually way a stronger acid than hydrogen fluoride. Of course, if you look at this trend, hydrogen fluoride is super weak acid compared to the rest of the three. Any guess? Make a quick guess. Why is hydrogen fluoride extremely a weaker acid compared to the rest? Look at these signs. They indicate this is way, way, way weaker than these three. It goes into the intermolecular forces of attraction and the bond strength itself. So what happens is hydrogen fluoride has hydrogen bonds in its molecules. We looked at that. Has hydrogen bonds in its molecules. So you need to first break the hydrogen bonds between hydrogen fluoride molecule and separate a molecule from another. Then again, break hydrogen away from fluorine. So with that, it prevents the ionization. In other words, there is excessively high energy needed to separate those two. So the hydrogen bonds prevents ionization, and at the same time, the hydrogen fluoride bond is stronger. We looked at that. In that way, it makes it very, very, very weaker acid. Looking at the remaining three, of course, the increase in atomic size can't be eliminated, and the increase in the bond length comes in, which decreases the bond strength, indicating HI will easily set free the hydrogen ions, becoming a stronger acid. So basically, that is it with the general physical properties. You notice we relied much more on the bond length and the bond strength. Actually, it is the most component when it comes to covalently bonded molecules like hydrides of group 7. It is one of the aspects you have to always look at. So let's go to one other aspect, which is the lab preparation. Lab preparation of hydrogen halides. A good point to note in here, you just need a suitable concentrated acid, react it with a halide. So acid bringing in the hydrogen ion, then the halide, of course, comes in with that halide, and they combine to form the hydrogen halide. So first, with the hydrogen chloride gas or hydrogen chloride fume, they are prepared by heating any halide salt, call it potassium chloride, call it sodium chloride, with concentrated sulfuric acid. We looked at this reaction when we were looking at the reducing powers of the halides with concentrated sulfuric acid. So in here, you will form your hydrogen chloride fumes and the salt. This is an illustration of what happened, you remember last time, and these are the fumes which are acidic. So of course, in this case, the hydrogen ion combines with the chloride in there. What about when you have hydrogen bromide and hydrogen iodide gases? How are they prepared? Unlike hydrogen chloride gas, here we use concentrated sulfuric acid. There are reasons, but let's first understand what happens. So you have any salt, mix it with the phosphoric acid, you will get the hydrogen halide that you're having in here. And so why isn't sulfuric acid used for these two? It's because the bromide and the iodide in these salts are strong reducing agents. We looked at this in detail. We saw the colors, so I do not need to stick much more on that. And this is the example of the reaction if you reacted sulfuric acid with any of these salts, you'll get such a kind of products. Let's now go to the last objective, which is on testing the halide ions. Reagents, as usual, we need silver nitrate and dilute together with concentrated ammonia solution. Procedure, add one reagent at a time and observe. So this is when you add silver nitrate. If you have any solution having a chloride, you would form this precipitate or this color. In the presence of a bromide, you see how the color is turning from white precipitate to yellow precipitate. This is actually cream. Some of us, you take milk, you know what is cream. So from white precipitate, cream, then to yellow. What happens if you add ammonia? Remember the procedure. Add drop by drop silver nitrate first, shake, observe, then add either dilute ammonia or concentrated ammonia solution. So when you add ammonia, this is why you observe. The white precipitate dissolves to form a colorless solution. Even here forms a colorless solution, but this does not dissolve. So let's make a conclusive statement in the observation. What is that compound that forms the white precipitate? I guess you're yet to ask, we did see the fluoride, what happens? For it, there is no observable change, so we do not normally include it in there. So for chloride, the white precipitate is because of the silver chloride form. Do you see the equation? Then, when you add it in dilute ammonia, it dissolves to form a colorless solution. You notice that. For bromide, the cream precipitate is because of silver bromide, as you see this one. This precipitate is insoluble in a dilute ammonia. It only dissolves in presence of concentrated ammonia to form a colorless solution. This is the colorless solution. And the reason is because the ammonia complexes up with the silver to form diamine silver 2 complex. So in that way, this is the complex in solution. But that will be in the next unit when we look at the transition methods. At the moment, just know when you dissolve the cream precipitate of silver bromide into concentrated ammonia, it forms a colorless solution. In the presence of iodide, it forms a yellow precipitate with silver nitrate, which also does not dissolve in the presence of dilute ammonia, but it also stays undissolved in the presence of concentrated ammonia. So in this way, you use these two reagents to identify a solution which has a chloride, a bromide, and an iodide. The presence of this colorless solution is simply because of the complex formed between silver ions in solution and the ammonia molecules. So that is it with the whole topic, your unit 12, which is about group 7 elements. I can't leave without giving you a wider exercise to test your understanding. I will actually start highlighting with the number 3, 2, and 1. So this number 3 tests your level of understanding and the application of knowledge. As you notice, it is asking, how does the oxidizing power of halogens change? Then predict which of the reactions is likely to occur. So you must be having the understanding for you to clearly predict such a reaction. And after predicting it, then give its product. So in this case, you need complete understanding. Number 2 is asking what happens if you add silver nitrate into those ions. And as you can see, this is what we looked at. This is simply simple understanding, and write the equations. Number 1 is much more of the comparison. You just need wide understanding. You're having hydrogen chloride is a gas, then sodium fluoride is a solid. We didn't look at the compounds of fluoride, but this is now where the understanding. With your knowledge of group 1, you should be able to apply this. Sodium fluoride is a solid, hydrogen chloride is a gas. What type of bonding exists in each? Explain in terms of bonding why their melting points are excessively different. This is a gas, this is a solid. Of course, this can be easily explained. Please go through those questions, discuss them with your friends.